Welcome back. Now we're on 18.9, occurrence, preparation, and compounds of oxygen. We're going to talk about oxygen compounds and preparation properties and uses of some representative metal oxides, peroxides, and hydroxides. This is the longest section from the chapter, so I apologize in advance. In my opinion, this should have been divided into either multiple sections or even been its own chapter by itself. So starting with just some oxygen facts, it is the most abundant element on the Earth's crust, making up about 50% of the mass. It occurs as O2 and O3. Those should be subscripts. O3 being ozone, O2 being oxygen, and forms about 20% of the mass of air. It's colorless, odorless, and tasteless, and slightly denser than air. It has a low solubility in water. It's slightly soluble, but this is very important for aquatic life. You need to have oxygen dissolved in water in order for fish to filter it out with their gills and be able to live. Commercially, it's isolated from air or through electrolysis of water. For air, take air, you cool it and compress it until it liquefies. But because oxygen has a higher boiling point than nitrogen, it stays as a gas and then can be separated out easier. You have to have oxygen to have combustion reactions. If you recall combustion reactions of hydrocarbons, you react them with oxygen to form CO2 and water. It's also needed for respiration, both in people, plants, all that fun stuff. Commercially, it has a lot of uses. For instance, oxidizing substances, removing carbon from iron during steel production, metal fabrication, cutting and welding metals, and that's done using an oxyhydrogen or oxyacetylene torch. It's made by plants via the process of photosynthesis, where plants take carbon dioxide from the air and water, and thanks to chlorophyll and light, they make that into glucose and oxygen. Ozone, which is O3, is made when dry oxygen is passed between two electrically charged plates and has a very distinctive odor. So when you have like a spark made from electrical equipment, that smell is due to ozone. It's very good when it forms in the upper atmosphere, in the stratosphere. And the reaction that occurs is UV light hits the oxygen to make it form O3, or an electric discharge, same type of thing. And so that gives us two O3s. This is an endothermic reaction, by the way, when it's formed. So that's the reaction when we have electricity, similar with UV. Most of it being in the stratosphere is formed in the stratosphere. This is a good thing because what it does in the stratosphere, you've heard of the ozone layer. It acts as a barrier to UV light from the sun by absorbing it and then going through chemical decomposition. So we showed how it's made, but then the opposite happens. It decomposes when it absorbs that UV light into single oxygen and then oxygen, the diatomic gas. So that reactive oxygen atom that's just by itself then will recombine with the molecular oxygen to reform ozone, and it's this ozone cycle. So having this nice ozone layer in the stratosphere decreases the frequency of skin cancer and other effects of UV radiation. However, it was found that chlorofluorocarbons, or CFCs, commercially known as freons, were damaging the ozone layer and depleting it in the stratosphere. Because what was happening is UV light makes them decompose to make atomic chlorine with this free radical that can then react with the ozone molecules, removing it from the stratosphere. It's not able to cycle. So Nowadays we have hydrofluorochlorocarbons, HFCs, something like that, to replace CFCs, but there's still some issues. We're still recovering. Ozone itself is used as a bleaching agent for oils, waxes, fabrics, and starches, and is a chlorine alternative for disinfecting water. This is the structure of the ozone molecule and some resonance structures to show its bonding. So some reactions. Elemental oxygen is a very strong oxidizing agent and reacts with most elements and compounds. Just a quick example. For instance, it'll react with magnesium metal to give us magnesium oxide. It directly reacts with all our elements except the noble gases, halogens, and some low reactivity transition metals, and reacts with everything except those at room temperature or at elevated temperatures if needed. When it reacts with the more active metals, it can form peroxides or superoxides. When it reacts with the less active metals and nonmetals, it can form oxides. So for instance, when it reacts with P4 phosphorus, we get P4O10. And I showed magnesium oxide, and then there's the phosphorus oxide, or P4O10 oxide. It does react with many compounds. It can, if you can oxidize any elements in a compound, they can generally be oxidized further by oxygen also. So, for instance, hydrogen sulfide has sulfur with an oxidation state of 2-. This is not sulfur's maximum oxidation state, so it could be oxidized by oxygen because of this reasoning. And so that reaction that occurs so now we give it some oxygen, we make some water, and SO2 gas. And got a couple interesting sentences here. It is possible to oxidize oxides that contain an element with a lower oxidation state. So if it has an element that has a lower oxidation state than oxygen in your oxide, you can oxidize that oxide potentially. Fluorine is the only element that can oxidize oxides to form oxygen gas, because fluorine is the only element that's more electronegative than oxygen. So we're going to talk a bit about oxides, peroxides, and hydroxides. Just to kind of introduce them, oxides have the oxide ion, which is O2-. Peroxides have the peroxide ion, which is O2-2-. Superoxides have the superoxide ion, which is a typo there. Oops, this should be O2-, like that. There we go. Sorry. So oxides is a single O2-. Peroxides are O2-2-, and superoxides are O2-1. And these superoxides have a bond order that O2-1 is a bond order of 1.5. Hydroxides have the OH- hydroxide ion. So starting with oxides, representative metal oxides are created by heating corresponding hydroxides or carbonates, but this is difficult to do with alkali metals due to the stability of their salts. They don't like to do this reaction. But just to start with a couple example, we take some aluminum hydroxide and we heat it. So we're heating the hydroxide here to form aluminum oxide. And similarly, we can take calcium carbonate. So hydroxides and carbonates we can generally do this with to make calcium oxide and carbon dioxide gas. The alkali metal oxides are better formed by redox reactions, which we do by heating nitrates or hydroxides with their metals. So, for instance, we take some potassium nitrate and we add some potassium metal and some heat. We get potassium oxide and nitrogen gas. So you can see we've made that metal oxide. Similarly, lithium hydroxide. So we'll do this with a hydroxide now. And with lithium metal, since that is our metal that we need here. And this gets us our lithium oxide and hydrogen gas. Peroxides of our metals that are in groups 2 through 15 we can make by burning that metal in air. Mercury 2 oxide is an exception. This is hard to do though for groups 1 and 2 because they can also react with nitrogen in the air. And so you end up with a mixture of peroxides and superoxides and nitrides. Sorry, this should be, they can form not peroxides and superoxides, they can form mixtures of oxides plus ionic nitrides. Ionic oxides themselves they have an oxide ion and they react with acids to form salts. There are some exceptions. And you can see those exceptions in your book, but I'm not that worried about it. So an example reaction, take some sodium oxide, react it with some nitric acid, and so we form a salt, a sodium nitrate salt, and water. That looks awful. Let me. There. Group 1 and 2 oxides and thallium 1 oxide can react with water to form hydroxides. So for instance, we take the thallium 1 oxide, so this is Tl2O, and water. That should say liquid, not aqueous water. There we go, and we get thallium hydroxide. You can also do this for sodium oxide or calcium oxide. The alkali metal oxides are really not used all that much in industry, but magnesium oxide is used to make things like fire brick, crucibles, furnace linings, and thermal insulation. Calcium oxide is also known as quicklime, and it's very reactive. When you heat it to high temperatures, it emits a very, very bright white light, and actually used to be used for stage lights in theaters before we had electricity. So this is where the saying of "in the limelight" comes from. So the oxide and hydroxides are inexpensive bases and used in chemical processes and processing as bases. We can make calcium oxide by heating calcium carbonate. So we take some calcium carbonate, which I think we saw this earlier. We give it some heat and we form calcium oxide and CO2 gas. Another type of metal oxide, alumina, which is Al2O3, is a mineral also called corundum, which is the major component for ruby and sapphire. Ruby gets its color due to a small amount of chromium present. What's kind of interesting now, other impurities are what gives sapphire its color. In the lab, they do make artificial rubies and sapphires by taking aluminum oxide and melting it with small amounts of other oxides to get the colors and that they want, and then it's cooled to produce large crystals. the ruby lasers, you tend to use synthetic rubies instead of using the naturally occurring rubies because it's basically the same thing and more controlled. Zinc oxide is a compound that a lot of you might be familiar with. It used to be used for a pigment in white paint, but pollutants can discolor it very easily. But it's used a lot in automobile tire and rubber manufacturing and in medical ointments. For instance, sunscreen. And zinc oxide is more of a controversial ingredient now, generally because it is present as nanoparticles and not very good for the environment, but it is a very good sunscreen. This is showing how limelight basically works with calcium oxide, giving it a flame to make it emit a nice bright white light. Here's someone putting zinc oxide on zinc oxide sunscreen so they don't get a sunburn. So peroxides and superoxides, these are very strong oxidizers and are very, very important for chemical processes. And we can make these when a metal or a metal oxide that's from group 1 or 2 reacts with pure oxygen at elevated temperatures. Sometimes you have to actually control the amount of oxygen to achieve the correct product. So one example of a basic reaction would be taking some sodium metal, reacting it with oxygen, and heat, and we get sodium Na2O2. And then another example, taking sodium, we'll look at strontium oxide. And now we get SrO2. One example of controlling stoichiometry or using controlled amounts is for peroxide, rubidium, and cesium peroxides. They need to have controlled amount of oxygens. For instance, for potassium, if you do 2 moles of potassium for every 1 mole of oxygen, you get K2O2. To get the potassium peroxide, but you can also get potassium superoxide if you have 1 mole of potassium for every 1 mole of oxygen. And one thing that's interesting to know is the stability of the peroxide or superoxide of the alkali metal in question is going to increase as the size of the cation increases. Next up are hydroxides, and these are pretty important for us. These are compounds that contain OH minus. We get soluble metal hydroxides by reacting the metal or metal oxide with water. The metals of group 1 and 2 will react with water to form hydroxides and hydrogen gas, with beryllium and magnesium being outliers. So for instance, if I take some lithium and throw it in water, I get some lithium hydroxide, it's aqueous, and H2 gas. Whoops. Now, these reactions can be pretty dangerous by taking a metal and throwing it in water. I've learned this lesson kind of the hard way at Cal State San Bernardino. One of the demos we do is we take sodium metal and put it in water for the students, and one time I added a little too much sodium and it actually kind of popped and went all over the place. And that's why we wear goggles even during demos. So if instead of reacting the metal with water, you can also react the oxide with metal, the metal oxide with water. It's a lot less dangerous. So for instance, we can take lithium oxide and react it with water to give us lithium hydroxide. So this is a bit safer to get our end product. Most metal oxides are actually base anhydrides, which is fairly obvious for like metal hydroxides, but other metal oxides are insoluble and don't form hydroxides in water, but they are still base anhydrous because they will still react with acids. Now, sodium hydroxide is very commonly used in industry. It's cheap, it's a very strong base, it's great. Sodium chloride tends to be the starting material used to produce it. And one thing interesting about NaOH is it is among the top 10 chemicals in production in the United States. It's mostly made by electrolysis of sodium chloride solutions via the chlor-alkali process. A little more about sodium hydroxide. It melts without decomposing. It is an ionic compound. It's soluble in water, gives off heat when you put it in water, and forms basic solutions. It's also used to produce other sodium compounds and used to neutralize acid during production of other chemicals. Hydroxides overall are used to neutralize acid as well as prepare oxides by thermal decomposition. Aqueous milk of magnesia, for instance, aqueous magnesium hydroxide in solution is milk of magnesia, which is used as an antacid. These hydroxides can also be used to produce salts when they are reacted with the appropriate acids. So in picture A here, you see a mixture of sodium hydroxide and zinc nitrate, and we get this white precipitate of zinc hydroxide. Whereas in B, we see it's okay. We're very proud of this B1. Addition of excess sodium hydroxide is going to result in the dissolution of the precipitate. So it's kind of cool. You add more hydroxide, and you can actually redissolve the precipitate. Calcium carbonate, aka Tums. Now, when it comes to non-metal oxygen compounds, most nonmetals do react with oxygen to form non-metal oxides. When it comes to common oxides with sulfur, we have sulfur dioxide and sulfur trioxide. The dioxide is made commercially by burning sulfur or roasting sulfur sulfide ores in air, which we just talked about this. The trioxide forms very slowly when we heat sulfur dioxide and oxygen together to give an exothermic reaction. The sulfur dioxide is a gas at room temperature and has a bent shape. And the trioxide is going to melt at 17 degrees Celsius and boil at 43. And what's interesting with the trioxide is in the vapor state, these are single unit molecules, but when we hit the solid state, they change to polymeric forms. So they become polymers. Both dioxide and trioxide can react as Lewis acids with other hydroxides and oxides, and in turn will form sulfites or hydrogen sulfites, and sulfates or hydrogen sulfates. Here's sulfur dioxide, which we just saw, and sulfur trioxide with its resonance forms. Halogens don't directly react with oxygen, but we can form halogen-oxygen compounds by reacting halogens with oxygen-containing compounds. So the oxides then will form with chlorine, bromine, and iodine because the oxygen is more electronegative. So chlorine, bromine, and iodine with oxygen form oxides. But with fluorine, we get a fluoride because fluorine is more electronegative, so it's no longer considered an oxide. These hydrogen-oxygen compounds are very reactive and unstable. The dichlorine oxide and chlorine dioxide are really the only commercially important compounds that can come out that we care about, and these are both used as bleaching agents. So here's our structures, Cl2 on the O on the left and ClO2 on the right. A little bit more. Now we're going on to non-metal oxyacids and their salts. The nonmetal oxides can form acids when they are allowed to react with water, and this forms acid anhydrides. And these oxyanions can then continue to react to form salts with metal ions. A couple examples, dinitrogen pentaoxide, N2O5, and NO2 both react with water and form nitric acid. This used to be called, nitric acid itself used to be called aqua fortis and is used to dissolve silver to separate it from gold. So even way back in the day, as in, is it like 5th century or something like that, this was known and used to separate silver because it dissolves silver but not gold. It's then made, it can also be made in the lab by heating nitrate salt with concentrated sulfuric acid, and that's nitrogen pentaoxide. Let's see, where was I? The Ostwald process is the commercial method used to make nitric acid. You take some ammonia and oxidize it to nitric oxide, which is then oxidized to nitrogen dioxide, and that's oxidized and hydrated to nitric acid. Before I get too far up, I want to show you taking nitrate salts and making nitric acid. So that second bullet point is all about nitric acid, again called aqua fortis, and we make it by taking some sodium nitrate and sulfuric acid and some heat, and you get NaHSO4 and HNO3, and there's our acid. So the Ostwald process, if you want to look up the 3 reactions that I was referencing, you can, but the overall reaction, when you add them all up, is you have 4NO2 gas plus oxygen gas plus water, and that gives us HNO3. But again, if you're interested in seeing all the steps, you can look it up in your book. One thing interesting about nitric acid is it very rarely forms hydrogen when it reacts with metals. Instead, the nitrogen itself is reduced, and the products that result depend on the concentration of your acid, the activity of the metal, and the temperature at which the reaction takes place. So this is showing you the structure of nitric acid, HNO3, as well as its resonance forms. A little bit more with nitric acid. It oxidizes non-metallic elements to their oxides and their oxyacids, and then in return will form NO2. You can take a 1 part concentrated nitric acid to 3 parts concentrated hydrochloric acid, and you form what is called aqua regia, which is a mixture used for dissolving gold, platinum, and other difficult to oxidize metals. So we take some NO2 minus and some H3O plus, oh, wrong reaction, but never mind. That's the wrong reaction. I was looking at the wrong spot in my book. I was like, wait a minute, here's the reaction. So when we add, for instance, some gold to this aqua regia, we can dissolve the gold in this complex here. And we form NO2 and water also. Now, nitrates are salts of nitric acid, and these form when you have some metals, oxides, hydroxides, or carbonates reacting with nitric acid. Nitrates themselves are the most water-soluble of the nitrogen compounds and very, very valuable as fertilizers. but there needs to be caution because they are very flammable. They are often used to add oh, where was I? Totally missed my spot. So these are, again, nitric acid salts, and these form when we have some metals, oxides, hydroxides, or carbonates reacting with nitric acid. Like I said, they're water soluble and very valuable as fertilizers, but they're flammable. They are also in gunpowder. So potassium nitrate is mixed with sulfur and charcoal to make gunpowder. Again, explosive. If we take some nitrite solution and add some acid to it, we make nitrous acid, which is a weak acid. So this is what I started to write earlier and went, oops, wrong reaction. NO2 minus, and we give it some H3O. We get nitrous acid, which is HNO2, and water. Nitrous acid is actually very unstable and only exists in solution. It can disproportionate into nitric acid and into its oxide. It is an oxidizing agent when it's given with strong reducing agents, and then will oxidize to nitric acid when in the presence of strong oxidizing agents. So depending what it's with will really determine a lot about its properties. And then sodium nitrite is used as an additive to meats, and this is done because it both limits bacterial growth and prolongs the meat's red color. There is a lot of controversy around nitrates and nitrites when it comes to the food industry nowadays, and that's because where was I? Because it can act, sodium nitrite can go back to nitrous acid, which can in turn react with organic compounds and form nitrosamines, which nitrosamines are potentially cancer producing in animals. So because of this, the FDA has limited the amount of nitrites that can be added to food. So I tend to, when I buy like hot dogs or something, get the ones that don't have nitrates or nitrites in them. But they're still usually in pretty low amounts where it's not too big of a deal. Here's the structure of nitrous acid. Next up is phosphorus oxyacids and salts, starting with phosphoric acid. It's got a few uses, but one of its main uses is actually as a soft drink additive. So if you look at your ingredients of a soda, most of them will have phosphoric acid. And this phosphoric acid, you can get it as an impure solution by treating calcium phosphate rock with concentrated sulfuric acid. It's not very pure this way, but you can purify it, or you can also get a more pure product by dissolving P4O10 in water. But the best way to make it is to hydrolyze phosphorus trichloride. So the reaction when we take that calcium phosphate rock, we have Ca3PO42, and this is reacting with sulfuric acid, concentrated, but it's still aqueous, even concentrated, and that gives us H3PO4, 2 of them, and some calcium sulfate. Again, the best method of making more pure phosphoric acid is to hydrolyze phosphorus trichloride. So we take some PCl3 and water, and that gives us phosphoric acid and some HCl. If you take the solution and heat it up, you remove the hydrogen chloride from it, the HCl, and then the water will evaporate until we get crystals of the acid actually forming. But if you then take those crystals and heat them up to 70.1 degrees Celsius and then let them decompose at 200 by direct disproportionation, you melt the crystals and they end up disproportionating into phosphine and orthophosphoric acid. So kind of back to your starting point. Disproportionation is pretty fascinating to me, actually. This is the structure of orthophosphoric acid, also known as just phosphoric acid. Again, it's colorless when it's pure, and then it has the molecular structure, Lewis structure on the right side. Now we have sulfur oxyacids and their salts. Sulfuric acid being one of our biggest ones, and we get this by oxidizing sulfur trioxide and then converting that to sulfuric acid. Sulfuric acid is very popular and used widely in industry, so much more so that there's more of it used than any other manufactured compound in industry. It's a very good dehydrating agent because it really does like water, so it'll take it out of something that maybe has some water contamination. It's a diprotic acid that can form salts and hydrogen sulfates. So sulfuric acid is pretty interesting, especially seeing it's diprotic. It's super strong. It's crazy to get like even a little drop on your butt, on your glove. You have to be really, really careful. I actually have a story when I was an undergrad. I had to use concentrated sulfuric acid for something, and I got a drip on my glove, and I could literally feel the heat of it reacting and eating away at it. So yeah, sulfuric acid's pretty crazy stuff. It oxidizes a bunch of compounds depending on the temperature and concentration of it and what the compounds are at. Sulfur dioxide dissolves in water, and this will form a sulfurous acid solution. But this is very unstable, and the second you add some heat to it, the sulfur dioxide starts to leave. Sulfurous acid is also a diprotic acid, interestingly enough. And sulfite and the hydrogen sulfite salts themselves are prepared by adding a stoichiometric amount of base to sulfurous acid solution and then evaporating the water off. So kind of interesting that we can make our salts, these sulfite salts, pretty similar to what we've done before. If you take sodium hydrogen sulfite and you heat it, you can form sodium sulfite as well as sodium dioxide and water. Oh, not sodium dioxide, that should be sulfur, excuse me. So we take some NaHSO3, solid sodium hydrogen sulfite, give it some heat, and we get Na2SO3 and SO2 and water. You add some oxygen to sulfurous acid and you oxidize the sulfurous acid to sulfuric acid, which is much more stable. And then what's interesting is that sulfites are very easily converted to sulfates. They oxidize super easy. So if you've got a solution with some sulfites, I can pretty much guarantee you at the same time you've got some sulfates present as well. Here's the shape of sulfuric acid. Around the sulfur in the center, you can see it's got a tetrahedral structure. It's got two of the oxygens that have H's on them and then two that do not. So now we have the halogen oxyacids and their salts. There's quite a few types. We have hypohalous, halous, halic, and perhalic acids. And these are the oxyacids that form between the halides and oxygen. So remember the halides, chlorine, bromine, iodine, and astatine, and fluorine. The hypohalous acids are the weakest and the perhalix are the strongest. One thing that's interesting is that hypofluorous acid is really the only known fluorine oxyacid, but it's really, really unstable, and the only way to make it is to react fluorine gas with ice. So you take some F2, react it with solid water, and you get HOF and HF. So from here, if you take some base and add it to hypohalous acid, you make salts that will contain the basic hypohalite ion, OX minus. And we can actually isolate these salts as solids, but they are unstable with respect to disproportionation in solution. But for something like hypochlorite, this is actually very slow. So hypochlorite is bleach. And then table 18.2 shows you the type of acid, the oxyacids. So like the hypohalous, so that would be, you could have hypofluorous, hypochlorous, bromus, iodus. Okay, and then we have halous acid, so we could have chlorous acid is really the only one that occurs. We have the halic acid, so which would be chloric acid, bromic, iodic. Perhalic, you'd have perchloric, perbromic, periodic, and paraperhalic, which doesn't seem to really occur except for maybe with iodine, paraperiodic. Some uses. The hypochlorite, generally it's as sodium hypochlorite, is used as bleach and a germicide. So generally it's made by performing electrolysis of cold, dilute, and aqueous sodium chloride solutions. So we can use that to get hypochlorite. Chlorous acid is actually the only known halous acid, and we can get this by reacting barium chlorite with dilute sulfuric acid. Chlorous acid is unstable and will decompose to chlorine dioxide, hydrochloric acid, and water. But it can react with bases to give salts that have the chlorite ion on them. Sodium chloride itself can be used as a bleach for paper because it's a strong oxidizing agent, yet it does not damage the paper itself. Chloric and bromic acids are only stable in solutions. Take them out of solution, they aren't so stable anymore. Iodic acid we get by reacting iodine with concentrated nitric acid. And then the lighter halic acids, we can make them by taking their barium salts and reacting it with dilute sulfuric acid. So if you recall, all strong acids, all these halic acids are strong acids and very active oxidizing agents, which makes sense. Hydrochloric acid we've looked at all the time, and we know that it's a very strong acid. These guys will react with bases to form salts that contain the chlorate ion. And these we can make them via electrochemical oxidation of a hot solution of a metal halide to form our metal chlorates. Some uses: sodium chlorate is used as weed killer, and potassium chlorate often used as an oxidizing agent. So they're definitely they definitely have their uses. Here's the structure of some of those chlorate ions. So you can see you've got your chlorine here, tetrahedral shape, 2 oxygens, and then these 2 lone pairs on the chlorine in the center. And then you can see more of a 3D structure as well as the Lewis dot structure. It's a very interesting structure. And these are the chlorate ions, ClO3 minus. Again, a pretty interesting structure. You have a chlorine triple with 3 single bonds of oxygen and a lone pair of electrons on it. And you can see what its shape and geometry also looks like. Perchloric acid is going to form when we take a perchlorate and we treat it with sulfuric acid under reduced pressure. So for instance, we take some KClO4 and give it some sulfuric acid. this gives us HClO4 gas and KHSO4 solid. So perchloric acid, this HClO4, put it in water, and now you get the acid. When it's in dilute solutions, it's pretty stable. But if you have it over 60% concentrated, it's actually pretty unstable and dangerous. The acid, perchloric acid, as well as its salts, are very powerful oxidizing agents because that chlorine has an oxidation state of 7+. It really wants to reduce an oxidation number, so it's ready to react. This is also the strongest known acid of all, so that's an interesting fact about perchloric acid. There do exist metaperiotic and paraperiotic acids, and these also have iodine in the 7+ oxidation state. These are very strong oxidizing agents, and they can react with bases to form salts. Here's the perchlorate ion, ClO4-, which again we get when we react perchloric acid with a base or by performing electrolysis of hot solutions of their chlorides.